Hello, welcome to this lecture, which is part of the TACO series on analytic techniques in directional geometry. I'm very glad to be given the opportunity to speak in this nice TACO's series. So what I would like to talk about is singularities of plurisubharmonic functions from the point of view of valuations. So it's something that goes back to originally work of Fab and Johnson in two complex variables, and that we then extended to the higher dimensional case together. And that also led to ramifications involving spaces of valuations that can be understood as Berkovich spaces. So we'll try to minimize the amount of sophistication here and take what I would like to be a rather gentle approach to the subject, focusing on Lelong numbers. So let me start by recalling a few facts on plurisubharmonic functions. Well, why do we care about PSH functions in the first place? So before answering that question, let me remind you that if you consider a smooth function on some open subset in Cn, then you say that phi is PSH, that stands for plurisubharmonic, if it's a complex Hessian, so the second order mixed holomorphic and anti-holomorphic derivatives that you compute at any point of omega is non-negative as a Hermitian matrix at each point of omega. But one reason these functions are interesting is when you compare them to convex functions, they are closely related to convex functions. And indeed, if you consider the case where phi only depends on the real parts of the complex variable z, so it's translation, it's invariant under translation by a purely imaginary vector, then PSH is indeed exactly the same as convex. So for the moment, I'm still assuming that phi is smooth, and we will soon mention the case of a possibly singular phi. So this is just because in that case, the complex Hessian is the usual real Hessian in the real variables. But the key feature of PSH functions compared to convex functions is that they enjoy a much broader invariance property to the following thing. So if phi is PSH and you pull back, you pre-compose by some holomorphic map F, then the composition here is going to be PSH. It's something which is not difficult to check based on this definition, because if you compute the new Hessian here, you will just compose that one by the complex linear map given by the differential of F at a given point. So that is going to preserve some hypositivity. But this is really an essential fundamental aspect of the subject, because it tells you in particular that, so again, for the moment, smooth PSH functions make sense on a complex manifold, on any complex manifold, because this is telling you in particular that being PSH is invariant under a holomorphic change of coordinates. Okay? And this is something extremely strong compared to convex functions, again, where you would need to compose your convex function with an affine map. And then in order to globalize the notion, you would need to work on a manifold whose transition functions are affine. This is called an affine structure. It's a very rigid structure. And of course, complex manifolds form a much broader class of interesting geometric objects. So as a key motivation to look at PSH functions, we have the relation they bear with the Kähler matrix. So as you may or may not know, but probably do, a Keller metric. So Keller metrics are precisely the metrics that are locally given, locally expressed as Hessians, complex Hessians of a PSH necessarily function phi. I'm saying that you pick some Hermitian metric on the complex manifold, and you pick holomorphic coordinates. Then your Hermitian metric corresponds to a Hermitian matrix at each point, and you've got a Keller metric exactly when this Hermitian matrix is locally the Hessian, given by the Hessian of a function phi, and then by positivity, this function is in particular PSH. Okay, so this gives us plenty of very important and interesting PSH functions. So let me give you a brief list, just to have a number of cases in mind. If you take the Euclidean norm on Cn, then what you get is, of course, the Euclidean metric, the corresponding Keller metric, the flat Euclidean metric on Cn. If you take instead the log of 1 plus z squared, you will get the Fubinish-2D metric, again on Cn, viewed as an open chart in the complex projective space. If you change now this with a minus sign, log of 1 minus z squared, you will get the hyperbolic metric on the unit ball in Cn. And as further interesting examples, also for what we're going to look at afterwards, take minus log of minus log z. Now z is one complex variable. So z is in the disk in C. And then you get the Poincare metric, the IDD bar of this, the corresponding Keller metric is the Poincare metric on the punctured disk. And maybe as a final example, something that has shown up quite a lot in Keller geometry over the last, say, 10 years, is the case of cone singularities. If you take phi, which is now this form, again, in the disk, this form, for some exponent 2 times beta, where beta is between 0 and 1, then you get cone metric on the punctured disk, which means that you, inside of C, which means that you are pulling the disk like that, and you are introducing an angle, a cone angle 2 pi beta. Okay, so we have all these nice PSH functions. So far, they've been smooth. And the topic of this talk is to tell you about singularities of PSH functions. So we definitely want to allow them to become singular. So in a nutshell, you could say that a PSH, a more general, possibly singular PSH function is one that can be written as a decreasing limit of smooth ones. That's what I can give you a more conventional definition. Singular PSH functions. So first, again, if phi is smooth as before, then one characterization of phi being PSH is that it satisfies the submean value inequality on any line. It's a subharmonic function on any line, complex line. So this is written like that for all z and a in Cn, such that the corresponding one-dimensional disk is contained in the domain omega of definition of phi. So that means that the restriction of phi, as I said, is to any affine, complex affine line is a subharmonic function. Okay, so now this is something that makes perfect sense for more singular functions, and this is the definition. This is the usual definition of a PSH function. So you can use this to define possibly singular PSH function. So that this is now going to be a function with values in R and possibly minus infinity, which is allowed, and you require that the function is upper semi-continuous. So the PSH function is an upper semi-continuous function that satisfies the sub-mean value inequality like that. And as a result, we can easily show that the corresponding function is going to be locally integrable, and it's also going to be locally bounded above, just because it's USC. And for what we are going to look at, as well assume that phi is a negative function, non-positive function. So being locally integrable means that we can look at its derivatives in the sense of distributions. In particular, we can look at IT bar of phi, which is then going to be a positive current. But I'm not going to rely on currents at all in this talk. We can forget about that. So a key fact that I mentioned before already, it's basically the first thing that you do when you define a PSH function. You show that you have a local regularization procedure, so that phi is PSH if and only if phi can be locally written as the decreasing limit of the sequence phi j of smooth PSH functions. I should have said that you exclude minus the function which is identically minus infinity on some component of omega in the definition here. So the same occurs in this kind of characterizations. You insist that phi is not identically minus infinity on some connected component. Okay, so this is simply obtained by taking a local convolution of phi with an approximation of unity. It's a very basic, important fact that is used all the time. So once you know this, for example, you get that pulling back or precomposing a PSH function by a holomorphic map is still gives you a PSH function. The PSH functions again are stable, preserved under pullbacks by a holomorphic map. And therefore, they make sense defined on any complex manifolds X. Okay. So now, let me give you a short list of fundamental properties of PSH functions. When now PSH function is allowed to be singular. Here is a proposition. If you look at the set of PSH functions on your manifold X, then this is a convex cone. You can take the sum, it's preserved on the sums and multiplication by a positive number. And it's also stable under the following important operations. So first of all, decreasing limits. If you take any decreasing sequence of PSH functions, and either it goes to minus infinity identically, or on some connected component of X, or you get a PSH function. Then it's also stable on the finite max. And if you want to go to infinite max, then you have to include the USC regularization, USC upper envelope. We are not going to use this so much, but if you take any family of PSH function phi alpha, you take the soup pointwise. This is maybe not USC, then you make it USC, you force it to become USC, it's the star operation, and the thing you get is a PSH function. Okay, so let me give you a few important examples of PSH functions that are now allowed to be singular. So the most important example of all is this 1 log of z. Z is any complex number. One complex variable. This is This is a subharmonic function. It's the fundamental solution of the fashion. And then if you compose by any holomorphic map, it's still PSH. So then you get that log of f, where f is any holomorphic function on X, on the manifold X. This is PSH function. Then you can take max of that, finite max. So if you have finitely many holomorphic functions here, you take the log of the max of the finite family, so some finite set fi of holomorphic functions. This is still PSH, and a variant of that, which is often used, is the log of the sum of squares. And we want to have so much here. Put it. So the log of that is PSH. You can write it as the decreasing limit as epsilon goes to 0 of epsilon plus the sum of fi squares. And this is PSH because it's obtained from the Fubini-Studi metric on Cn that we saw before by scaling and putting back by a holomorphic map. Okay. So these two here, the log of max and the log of the sum of fi squares, they have the same singularities, meaning that the difference between the two is a bounded quantity. And these type of singularities, the last two, are called analytic singularities, because they are defined by finitely many holomorphic functions, or if you want, by an ideal of holomorphic functions, or coherent ideal sheaf on X. Okay. Now, a particularly important class of PSH functions for our purpose is the following. So it's the toric case, which was somehow already mentioned before. So here you assume here that omega in Cn is invariant, your domain is invariant under the torus T, the compact torus T, which is S1, n copies of S1, that of course is acting on Cn. So this is classically known as a Reinhardt domain. And then it makes sense to ask for a function phi on omega to be T invariant. Okay, so this is the classical terminology Reinhardt domain. It would nowadays maybe call rather toric domain. It belongs to the realm of toric geometry. And then you can consider function phi on omega. We'll say that phi is toric if it's T invariant itself. And then phi for a toric function being PSH is the same thing as being a convex function of the log of the zi's. Okay. And I put a minus here for convenience. It's not the main point. So I'm saying that if you have a function which is S1 invariant, it means it only depends on the absolute values of the zi's, or on the log of that if you want. And the corresponding function is convex. It's a convex function on some appropriate open subset of R to the n that corresponds to the omega here. So in practice for us, we are going to use this for when omega is a polydisk, and the corresponding domain is R plus to the n. It's an ortant in Rn. So this is very simple to see. I've already mentioned that a PSH function that only depends on the real part of Z is exactly a convex function. And here you just perform, you pass to the exponential coordinates, and you get this in a direct way. Okay. So as an example, among the functions we saw before, so the potential of the Poincare metric on the punctured disk, and also the potential of a metric with cone singularities in the disk, and both are toric PSH. Well, or just SH here, subharmonic on the disk. Okay, so here chi is just minus log t, and here it's exponential minus 2 beta t. Okay, so now we want to analyze the singularities of a PSH function, which is not necessarily toric. And this is basically the topic of neural numbers that occupies most of this talk. So you pick phi PSH function defined near the origin in Cn. So of course, it could be and it will be near a given point on a manifold, but if you choose coordinates, then you are reduced to this situation here. And because we are interested in the singularities, we can just add a constant to phi. It doesn't change anything. And because phi is locally bounded above, we can assume without loss of generality that phi is non-positive. Just simplifies presentation tiny bit. Okay, now the first case that we look at is this case here. So suppose that phi is toric. Phi is toric, as we just saw, it can be written as chi of minus log of the moduli of the coordinates. And here chi is now going to be a convex and non-positive function on some orthants that you need to push far enough, because the function phi here is only going to live on a small enough polydisk about the origin. So that means that you get a function which is defined on something like that, some far enough translation of the orthant R plus to the n. Okay, then we want to encode the behavior of chi at infinity. We want to look at the slopes of chi along rays that go to infinity. And the set of directions that is allowed is a cone, and it's just the orthant itself. So the R plus to the n, you forget about A. R plus to the n is the cone at infinity of this domain of definition of chi. And so what we're doing here is it's called homogenization. To introduce the function chi hat on R plus to the n, which is here going to be a non-positive function because chi already is. So chi hat is a convex and homogeneous function, positively homogeneous. So chi hat of t times something is t times chi hat of something, where t is a positive real number. And so this function here is the smallest with these properties, such that the following holds. So basically such that chi hat is greater than chi, that we have to shift by A like that because of the fact that phi is only defined near the origin from a small polydisk. Okay, then we can write down an explicit formula for chi hat. And it's, as I said before, it's exactly given by the slope at infinity in the direction of W here. So you look at the increment from A to A plus T omega W of chi, and you divide by T. So that's the slope of a convex function. It's an increasing quantity, and it increases to something which is chi hat of omega. Okay, and because chi is non-positive, you directly get this inequality here. Okay, so it's something, as I said, that encodes the behavior at infinity of chi. It gives you the slopes at infinity. As an example, just to show that you can have a singular function for which this is trivial, but the function itself is still singular. But pick the the Poincaré potential in the puncture disk, so the log-log singularity, then chi of t is minus of t, and then chi hat is just going to be 0 because the slope of the convex function that decreases at the log rate is 0. So chi hat is only detecting linear decay of chi, which corresponds to a logarithmic singularity for the function phi. That's the idea. Okay. Then we move on to the general case, and then we have a very simple recipe to reduce back to this first situation. We can turn any PSH function into a toric one in a very simple way. So recall that phi is just any PSH function near the origin in Cn, so say on a small polydisk centered at 0. And then what you do is the following kind of averaging procedure. So T is still the compact torus, T is still my S1 to the n, which is acting on Cn, and you take the soup along the orbits of the torus. And we saw before that if you take a soup of PSH functions, then either if it's already USC, but here T is compact, so it's not hard to show that this is already a USC function, and this is going to be a PSH function. It's the USC upper envelope of a family of PSH functions. So then this is a PSH and toric function of Z. We have turned phi into a toric function, and then we can apply the step 1. So 1 gives us, so this one can be written as chi of minus log of zj's, as in the first step. And then we will set phi hat. We define phi hat to be just the corresponding function chi hat. Okay? It just means that I don't want to always remember this notation chi when phi is not toric. So I start from a PSH function phi and associate to it phi hat, which is a convex and a homogeneous function on R plus to the n, which is encoding the slopes at infinity of this torification of phi. Okay, so what we've just been doing here is exactly the business of classical Lelong numbers and chiselman numbers, which play a key role in the story I'm going to tell you today. And indeed, you can check, you can give the following description of phi hat. Pick some weight W R plus to the n. So I should have said that R plus here means that it's positive or 0. I allow some of the WI's of the entries to vanish. Okay, then from the previous definition, and maybe using also the maximum principle for phi, which I should have mentioned somewhere, it's not hard to show that minus phi hat of W, which is non-positive quantity, can be described as follows. It's the greatest gamma, non-negative gamma, such that phi is more singular, and meaning more negative here, than gamma times a certain model function. So you could also add some bounded term. It doesn't change the description, but the point is that in fact we can arrange for this to be uniform and even 0. And what is psi W? Sort of model singularity with corresponding to the weights W is given by the following formula. You basically take the max of the log of the zi's, but you just look at the zi's for which wi is non-zero, and you weight in this way by 1 over wi. Okay, so the quantity here This is called the chiselman number of phi at the point 0 and with weight W. And the main first, say, historical example, and probably still the most important one, if you take all the weights to be equal to 1, then you get exactly the Lelong number of phi at 0. Then it's the greatest gamma such that phi is more negative than gamma times log of z. And this you can also think of as the vanishing order of exponential phi, if you want. So phi is allowed to become minus infinity at the point 0. So exponential of phi is vanishing, and you want to measure how much it vanishes. And this is the Lelong number. But in fact, so using this procedure, very simple procedure of turning phi into a toric function, we directly get all the chiselman numbers, the weighted Lelong numbers, and you will also directly get the convexity with respect to W, which is a classical property of the chiselman numbers. So none of that is particularly original, of course. It's just ingredients that were used many years ago to define these quantities. But let me give you one important proposition that has to do with what we've just done. We've turned a PSH function phi, to a PSH function phi, we've associated this function phi hat, this convex homogeneous function phi hat. And this transform takes phi to phi hat has the following properties. It's additive, it's homogeneous, again, of degree 1, and with respect to multiplying phi by a positive number. So the two properties means that this is behaving as we want it to behave on the cone of convex cone of PSH functions, and it commutes with the max. But the last two properties are homogeneity is very trivial, and even this one that it commutes with the max, it's very simple to check. So the only thing which is non-trivial here is additivity. Okay, because we have taken a PSH function phi and we have turned it into a toric function by taking the sup over the orbits of the torus. And the sup of the sum is, of course, not the sum of the sup. So a priori, there is something to check. But the trick, which is again something very classical in the subject, is that you can replace in the definition of phi hat, you would get the same thing if you replace what we've been using, which is the sup over the orbits, with the more standard averaging procedure where you integrate along the orbits. So instead of this sup, you take integral of phi of I theta z on the torus. And this is the Haar measure on the torus. You average phi with respect to the torus action. And okay, so why can you replace this one by that one? So let me be brief. This is a consequence of the Harnack inequality. So let me very briefly say that, say you look at the one complex variable case, you have a subharmonic function. It satisfies the submean value inequality, and then you can improve the submean value inequality by introducing the Poisson kernel, and then you can really bound from above your PSH function, your subharmonic function in a given disk in terms of an integral on the boundary of the disk against the Poisson kernel. And using that, you can show that the sup on a slightly smaller disk is controlled from above by a positive multiple of the mean value on the boundary. Okay, so the point is to be able to control the sup here from above by this quantity, the mean value. Okay, so it's, of course, the proof should be longer than that, but once you have the Harnack inequality, it's not difficult to conclude. And of course, we now have additivity because this integral is of course linear with respect to phi. So if you are allowed to do this and get additivity as well for the chiselman numbers of p hat. Okay, so now the chiselman numbers, it's also something that is very classical from the more algebraic point of view of valuations. So it's the transition now to the world of valuations. Maybe you won't see them so much, but let me mention the following fundamental case. So you take a PSH function, which is the log of a holomorphic function. So f is a holomorphic function near the origin in Cn. We consider the corresponding PSH function. And then you will, for a weight W, you will define val W of f as the chiselman number with weight W. So that's minus phi hat. So you may wonder why not put the minus sign in the definition of phi hat, but you will see why at the end of the talk. Okay, so I'm claiming that this is a valuation, and it's a monomial valuation. So what does it mean to be a valuation? First of all, so we have the following properties. The first one is a reflection of the additivity that we just sketched before. If you take the value on the product of two functions, you get the sum of the values. And on the other hand, if you take the value on the sum of two functions, that basically corresponds to the max of the function, but not exactly. Well, anyway, you will get that this is greater than the mean. So this we think of as corresponding to the fact that this commutes with the max. And indeed, I mean, you can refine these sort of things, replacing the function with an ideal and then really recover equality here. Let me not get into this. So just these two properties follow from the previous proposition, and they are telling us that val W is a valuation, real value valuation on the ring of holomorphic germs at 0. These are the two properties of evaluation. And you can be more specific for this particular valuation if you expand f as a power series. Then you can show, using, for example, this description here and the Parseval formula, various other tools, I guess, you can prove that in fact this valuation is given by the following formula. So you look at all monomials Z alpha that do occur in the expansion. So A alpha, the coefficient A alpha is non-zero. And then you have a certain, well, this is sum of alpha I Wi, the usual scalar product. So it means that this is the valuation of W of the monomial Z to the alpha with respect to val W. Okay, so it's a valuation which is determined. Val W of S should always be greater than the mean here, and here you have equality. So it's completely determined by its values on the monomials, and for this reason it's called a monomial valuation. So the monomial valuation with weight W. It's the weight vector, the weight you put on each coordinate Ci. And these monomial valuations, they play a central role in toric geometry when you want to define the fan of a toric variety. One way to understand the fan is in terms of valuation, monomial valuations like that. Okay. So now that we have this local way of encoding part of the singularities of the PSH function into a convex function, we would like to globalize the procedure. Globalizing means the following thing. It will be done in 2 steps, in fact. We want to globalize the construction. In the first step, we assume that phi is PSH on a complex manifold X. And we consider a divisor D. Which is a simple normal crossing divisor, SNC divisor. SNC stands for simple normal crossings. So that means that the DIs, this is the irreducible composition. So the DIs are smooth, connected, or irreducible. It's the same hypersurfaces. And the intersections, they intersect in a transverse way. So the notation is that dj, which is the intersection of the di's for I in j. If you pick any subset j of capital I, with an intersection, this is a smooth subvariety as well. Transverse intersection of normal crossings. Okay. And we will also assume for simplicity, it's not something which is so essential that we can always reduce to this situation anyway. So for simplicity, we will also assume that dj is connected. And any such intersection like that is connected. So we want to avoid, just for the sake of simplicity, we want to avoid the case of two things intersecting in this way. Okay? As I said, without loss of generality for what we're going to do, we can assume this, and you pick a point, you pick any point P in this intersection dj, you assume that this is non-empty for some j, then this is called a stratum, and you pick a point, any point in dj, and then you can find holomorphic coordinates at P, D1, Dn, such that, well, first of all, say the first, such that the indices j that cut out dj, they correspond to the first, say, m indices, and di is locally given at P by zi equal to 0 for I and j. That comes from the normal crossing condition. That it's the definition of the normal crossings. And gives you this. So it means that near the point P, we are exactly back to the Cn situation, and we have selected a certain subset of the hyperplane coordinates. And then we can apply the previous procedure. We can apply the previous procedure. So what we get, working at the point P for the moment, we get a function P hat, which is convex and homogeneous on, so it's defined in fact on all of R plus to the n, and it's also defined on the subcone R plus to the j. Okay, so here I'm identifying R plus to the j with R plus to the m. It means that the last n minus m coordinates are vanishing. So this is sitting as a subcone of that cone. But the point is that I want to force the weights outside of j to be equal to 0, because then something very interesting happens, is that the construction here becomes independent of the choice of P. And so I'm not going to do that in detail, but so it really follows from the properties we saw before of phi hat, and basically basic facts, basic properties of convex functions give us that, and plus, okay, previous things plus the connectedness argument can show that phi hat restricted to R plus the j is independent of the points P in dj. here, dj could really be a big submanifold, so it's not just moving locally at P, but the point, you show that the set of points for which this is independent of P is open and closed, basically. Because we assume that dj is connected and gets independence along the whole of dj. So as an example, if j is just one in index 1, we have one particular component d1 in x, which is a reducible hypersurface, then phi hat on the corresponding thing here is just basically a number, because this is just a ray, one ray, and this is corresponding to the so-called generic Lelong number of P along D1. But to justify the terminology, we need to get into less trivial properties of the Lelong numbers. So a deep result of Su that was proved in the late 70s and then given a simpler approach by the Mailly, building on multiplier ideals, is that if you take the Lelong number at a point of a PSH function, then this is something that depends in an upper semi-continuous way on the point with respect to the so-called countable Zariski topology, for which closed sets are at most countable unions of Zariski closed subsets. And then using that, you can show that if you move along a divisor, D1 like that, then the value of the Lelong number at a point is equal to the infimum for almost every point in D1. And so it's really the generic value, and it corresponds to this number here. So if you want to be a bit more concrete, so if phi is log of f, where f is a holomorphic function, it's really the vanishing order of your holomorphic function along D1. Okay. But what I'm saying is that this independence of P, the fact that it's independent of P, it holds also when you cut out a higher codimensional subvariety by several transversely intersecting hypersurfaces. Okay. And then, because we have this nice function that lives on these cones, we get also a function on the union of such cones, which is an object that is considered a lot, which is attached to an SNC divisor D as here. So we get, as a result, phi hat, which is a function on the fan. The fan is a union of cones. And the fan here is the union of the cones R plus to the J inside of the ambient vector space R to the I. And you take the union of all cones that correspond to a stratum, meaning for a subset J such that the corresponding intersection is non-empty. And if you want to think of this in a more direct way, you should view this vector space as the dual of the vector space of real divisors with support in D. Okay, so I'm going to give you a flavor of this object. Suppose that the divisor D has three components. Say it's three curves on the surface that intersect like that. Then you consider the dual graph of that. So you get an edge, a vertex, I'm sorry, for each of these curves, E1, E2, E3. And each time they intersect, you join them with a line segment. And that thing, so this is the dual graph, and this is the cone over it. So in this cone construction, you add an origin. And here you get the cone that corresponds to the stratum here, the intersection of D1 and D2. This is the first cone. And you have the second cone. that corresponds to that stratum there, to 2 zero-dimensional strata. So this sort of object is considered a lot in various settings, but it's basically, we are basically doing toric geometry locally, so this is called toroidal geometry. Okay, so let me summarize. What we've done here is that we have phi, which is PSH on X, and we have some SNC divisor D. Then we have this gadget delta XD, which is a union of cones, fan, that is attached to it, and we have a function phi hat here, which is homogeneous and which is convex on each cone of the fan. And this function phi hat is encoding weighted Lelong numbers or chiselman numbers with respect to the local coordinates given by local equations of the components di, the di's of components of D. Okay, and then we can globalize even more by trying to look, by allowing to pass to a higher birational model. So suppose now that's second step. Suppose now that we have another such SNC pair. So SD here would be called an SNC pair, manifold plus an SNC divisor. Suppose you have another one SNC pair that dominates XD in the sense that that you have a map from X prime to X, a holomorphic map, which is proper and bimeromorphic, generically an isomorphism over a Zariski open subset of X. And you assume that also the pullback of D is supported in D prime. So D prime is a bigger divisor than D. You have D, you take the strip transform of D, and also you add in the exceptional divisors, and the thing you've got is supported in the bigger divisor of D prime. Okay, then then you have, of course, a map which you can pull back divisors. So you can take a divisor on you can take a divisor on X with support in D. This is the space we were quickly mentioned before. And you can pull back by mu to get a divisor supported in D prime because of this condition here. And this is a linear map, so it induces a dual map on the dual space that I denote by mu. I'm not sure this is such a good notation, but mu lower star. Okay, and inside of that, I've got my fan attached to D prime, and here the fan attached to D. And you can easily show that the fan on the left is mapped to the fan on the right. So this mu lower star maps delta of X prime D prime to delta of XD. So it's a functoriality property of the previous construction. If you have an SNC pair, you have the corresponding fan. And if you pass to a higher SNC pair that dominates it, then you get a map from the fan of the dominating pair to the other one. Okay, now I'm claiming some things. I'm not going to explain this, but it's not so hard to check, in fact. So now if you still have phi, which is PSH on X, then you can do two things. You can look at phi hat. So you can take the corresponding function phi hat on delta of XD. but you can also pull back phi by mu and take the corresponding convex function, well, a homogeneous function, on the fan of x prime d prime. Okay, but then of course the first one you can also pull it back by this map here, and I'm claiming that there is a natural inequality between the two. Then so the claim is that this holds true. So these two ways of getting a map upstairs satisfy certain monotonicity for this inequality here. So the idea is that the more negative phi hat is, the bigger the Lelong number, so the more singular the function is. And the idea is that if you look at the singularities, after pulling back to some blowout, you see more of the singularity of phi, so you get something which is more negative. That's a bit of the moral behind the inequality. Okay, and now the game you can play is to allow not only one SNC pair, but you can look at all SNC pairs over a given point, which means that you allow to blow up as much as you want to extract as much of the singularity as possible from the point of view of Lelong numbers. So one example, one situation that you can do this is you assume that phi is PSH near points, so say near the origin in Cn, as we had before. And then you can look at, you can consider SNC modifications of that, which are SNC pairs. So here, this is a birational, again, a proper birational map, and the divisor D, this is an SNC pair that lies over Cn, comma, the origin, meaning that D is mapped to the origin by pi. So what you're doing is that you are blowing up the origin in Cn, you get some Pn minus 1 at the first exceptional divisor, and then you blow up something in the first exceptional divisor, you get another one, and so on and so forth. And this way you can basically reach any SNC pair like that. This dominates any such SNC pair. So you can think that P is a composition of nice blowups of smooth subvarieties. And this forms a directed family. We just saw before that there is a notion of SNC pair that dominates another one. So among all these SNC modifications, there is a natural order by domination. And every time you pick one, you have phi hat xd, which is the function. You take phi here, you pull back by pi, and consider the corresponding homogeneous function on the dual fan xd. So I denote it now by phi hat xd. Okay, and now you want to take into account, as I said, all possible such SNC modifications. So you are going to introduce the limit of that. There are two ways of doing it. It's a bit tricky to explain. I'm not going to be very detailed here, but we can come back to this in the discussions later on, for example. But then what you get is that when you introduce V of Cn in 0 to be the projective limit of all such dual fans attached to SNC modifications. So the limit is over all SNC modifications of Cn, 0. We have an inverse system because of the maps that project delta x prime d prime to delta xd when x prime d prime dominates xd. We can take the inverse limit of that. And it follows from the works of various people. For example, you can see a version of that in well, I guess in our paper with Matthias and Charles, that this is isomorphic. This can be understood as the space of semi-valuations. Semi-valuations centered at the origin in Cn, which is a certain instance. So it's a space, semi-valuation means that it's like a valuation that you allow the value to be plus infinity, maybe not only on 0. And this is a special instance of a Berkovich space, a non-Archimedean analytic space. They are typically obtained as spaces of semi-valuations. So you can identify this inverse limit as this with the space of semi-valuations. If you want this structure results, if n is equal to 1, then this is basically a cone over a graph, as we saw before, and you have an inverse limit of graphs, which is for n equal 1 will in fact be a tree. It's an R tree that you get. So you get a cone over an R tree. Okay, and now what happens is that every time you have xd, we have this function phi hat xd on delta xd, and we have this monotonicity. And if this is dominating, if x prime d prime is dominating xd, then phi hat on x prime d prime is less than or equal to phi hat xd composed with map mu. This is what we saw before. So then you can extend those functions by monotonicity to a function on the big space here. We get the function phi hat, which is the decreasing limit of the phi hat xd on the whole space of valuations, of semi-valuations. So that you can call, if you want, the valuative transform of phi. It takes into account all the real numbers and all models. So to give you a flavor of what is encoded in this function, here is a result that we proved with Charles and Matthias. It's a characterization in terms of multiplier ideals. So I should probably have said a word about that, but there is not so much time left. So let me assume that you've already seen a multiplier ideal before, or otherwise we can discuss it later on. So if you take two PSH functions, P and C, near the origin in Cn, then the two functions that you get on the space of valuations are going to be equal. So it's valuative equivalence, if you want, of phi and psi, if and only if they have the same singularities from the point of view of multiplier ideals. So here, I of t phi is the multiplier ideal of t times phi, where t is some positive quantity. And then you want this to be true for all t's. So what we're saying here is that you can compute a multiplier ideal in terms of the Lelong numbers or the corresponding function phi hat on valuations. And so this would tell you that if the two functions have the same Lelong numbers, then we have the same multiplier ideals. And conversely, you can approximate a function phi by its multiplier ideals. This is something developed by Demailly. And this approximation is good enough to capture the whole function phi hat. You can recover phi hat entirely from the data of its multiplier ideals, like this. And let me just conclude with a question here, a problem which is rather important. So I should have said that this sort of things, so related consideration has been playing an important role in the proof we gave recently of the Yoit and Donaldson conjecture for the existence of Keller-Einstein metrics with Berman and Johnson, in which we exploit really this point of view of associating to a PSH function or a PSH metric, a non-Archimedean function, a function on the space of valuations. And it would be very interesting to get an answer to the following question. So suppose now that you take some normal singularity at the point 0 in y. So before we had y equal to cn, and here we would have something a bit singular, even canonical surface singularity or KLT singularity would already be very interesting. And then you have some PSH function near the origin at that point in y. So there is a notion of PSH function on a normal complex space, or even any complex space. And then using the previous construction, you can also define a function phi hat on the space of valuations. And okay, so the conjecture is that there should exist Pj. You should be able to write Pj as the decreasing limit of PSH functions with analytic singularities. So of the form log of the max of finitely many holomorphic functions, in such a way that the corresponding valuative transforms converge. So this is true when y is non-singular, precisely using multiplier ideals. So you look at the functions that are associated to the multiplier ideals, and they satisfy this property. This is something that lies behind this theorem. But similar technology cannot work in a singular situation, because even in good cases where you can define the multiplier ideal, it's not true anymore that the multiplier ideal is less singular than the function phi you start from. So this is really something that would require, it seems, new ideas and lead to a new understanding of PSH singularities on a singular variety. So I will stop here. Thanks a lot, and see you soon on Gitter and so on.